SwayamPrabha. Digital India. Educated India.
Welcome to the DTH sponsored course on micromachining. I am going to talk about micro nano abrasive finishing technologies and overview, and I will deal in detail slightly about the abrasive flow finishing process. Organization of the talk, I will give you some glimpses of nano finishing technologies, acknowledgement, and some related books. What is micromachining? Very briefly I will tell you, because I have in detail discussed it in the introduction part. Nano finishing, advanced abrasive micromachining finishing processes, abrasive flow machining or abrasive flow finishing, and classification of abrasive flow finishing processes, how to enhance the performance of abrasive flow finishing processes. I will put some light over there. Then I will deal with the conclusions. In other two lectures, following processes will be discussed in reasonably well details: magnetorheological abrasive flow finishing, rotary magnetorheological abrasive flow finishing, chemomechanical magnetorheological abrasive flow finishing, magnetic float polishing, alid grinding, and conclusions. Acknowledgement: all those who have contributed to nano finishing research at IIT Kanpur, Dr. R.K. Jain, Dr. Sunil Jha, Dr. Vijay Gaurana, Dr. D.K. Singh, Dr. S.C. Jaiswal, Dr. Manas Das, Dr. Ravi Shankar, Mr. Ajay Sitpara, Mr. Prabhat Ranjan, Mr. Pavan Vasera, Mr. Satish Kumar, and Mr. Mithun Sarkar. The work done at IIT Kanpur was sponsored by different agencies in India. They are BARC, Trombay, Mumbai, DST, New Delhi, ARDV, Bangalore, and CSIR, New Delhi. Sorry for repetition, if any, of some slides in these three lectures, this lecture as well as following two lectures. A book on nano finishing science and technology edited by B.K. Jain has been recently published, and it deals with most of these nano finishing processes in detail, along with the scientific aspects of these processes. Majority of the material discussed here has been taken from these books, like advanced machining processes, micro machining, micro manufacturing processes, and mainly nano finishing science and technology, published by CRC Press. This is the second edition of the book, Machining Technology and Advanced Machining Science. And this is the second edition of Introduction to Micromachining. What is micromachining? Micro nano material removal processes. They are micro nano machining and then micro nano finishing. Please note it carefully. In finishing also you are removing the material at micro nano level, but here you are changing the surface structure. But when I say micro nano machining, here you are trying to create features also on the component being machined. So traditional machining processes, advanced machining processes, both have been discussed to some extent, and some aspects of them from finishing point of view will be discussed in this lecture. Micromachining, I will not go in detail, I have already discussed it. Micro plus machining, removal of material at micro level, macro components, but material removal is at micro nano level, and micro nano components and material removal is at micro nano level. For example, MEMS, micro electromechanical system, NEMS, nano electromechanical system. You can see here, this is the leg of the fly and these are the different components. So you can imagine what is the size of these components, and definitely they are in micron size. Unfortunately, the present day notion is machining of highly miniature components with miniature features. Literally, it is not a correct definition of micromachining. In my opinion, more correct definition is material removal at micro nano level with no constraint on the size of the component, because if you see the word micromachining, micro plus machining, it does not include any constraint on the size of the component, whether it is macro size, meso size or micro size. Nano finishing, material removal at micro nano level. We will have an overview of some advanced abrasive nano finishing processes. Please note it, I am deliberately telling abrasive nano finishing processes because I am not including non-abrasive nano finishing processes, just like electrochemical polishing and other processes are there where you are not using abrasive particles, but still you are able to achieve very good surface finish. Micro nano finishing, they can be divided in two categories: traditional and advanced, grinding, lapping, honing. But with all these three processes, there is shape and size constraints or limitations with each of these traditional finishing processes, and that is the reason why these advanced nano finishing processes were developed, like abrasive flow machining or abrasive flow finishing, magnetic abrasive finishing, magnetorheological finishing, magnetorheological abrasive flow finishing, chemomechanical magnetorheological abrasive flow finishing, electrolytic in-process dressing and grinding, magnetic float polishing and chemomechanical polishing. So these are the different advanced nano finishing processes. In some of these processes, you can achieve even sub-nano level surface finish. We will discuss them in detail. And then electron EEM processes. Only abrasive based advanced finishing processes are discussed here. Now here EEM, elastic emission machining, and this can give very good surface finish of few nanometers. Advanced abrasive finishing processes, I have just told you in the earlier slide, these are the different names of them. Now here you can just see, this is the irregularity on the surface to be finished, and this is the abrasive particle which is coming in contact with the surface irregularity. So two forces are acting simultaneously. This is the normal force which is responsible for penetration of this abrasive particle into the workpiece surface, and cutting force or FC force is responsible for shearing of the irregularity and creating microchips or even nanochips, depending upon what is the indentation of this abrasive particle into the workpiece surface. In all these processes, normal force is responsible for penetration of abrasive into the workpiece, and shear force is responsible to remove material in the form of microchip, that is the microchip. Now here we are not considering the effect of chemical reactions in chemomechanical magnetorheological finishing, chemomechanical polishing, electrolytic in-process dressing. Only I have touched superficially some of the reactions etc. in these processes, but detailed chemical reactions I am not going to tell. Rather, I am just basically concentrating in these lectures on the mechanical abrasion finishing process. Classification of nano finishing processes. Traditional nano finishing processes I have just shown to you. Advanced nano finishing processes. These are the further classification. General advanced nano finishing processes like abrasive flow finishing, elastic emission machining or elastic emission finishing, elastic abrasive finishing, focused ion beam finishing. I have not mentioned it in earlier. With the help of this, you can achieve surface finish of nano level only or sub nano level. This is not a recommended process for micro level surface finish. Magnetic field assisted advanced nano finishing processes, magnetic abrasive finishing, double disc magnetic abrasive finishing, magnetorheological finishing, magnetorheological abrasive flow finishing MRAP process, nano finishing of free form surfaces using ball and magnetorheological tool BEMRT and magnetic float polishing. There may be other processes also which may not be here, so I don't claim it to be exhaustive, but this is general classification of different types of nano finishing processes. Hybrid advanced nano finishing processes, electrochemical grinding where ECM plus grinding work together, electrochemical magnetic abrasive finishing, magnetic MAF plus electrochemical machining, electrochemical honing of gears, electrolytic in process dressing grinding, chemo mechanical polishing, here chemical as well as mechanical, chemo mechanical magnetorheological abrasive flow finishing. It includes three processes, CMP plus MRF plus AFF. All the three processes are acting simultaneously, and then you have electric discharge diamond grinding. Again you have two processes, EDM plus grinding. Same thing given in the schematic viewpoint of view. Traditional rigid tool, floating abrasive lapping, CNC 3 axis, 4 axis, 5 axis, robot based degree of freedom, 2 degree of freedom, 3 degree of freedom, 5 degrees of freedom and so on. So you can further classify them. Non-magnetic polymer based AFF process, EEE, E-ball AF, EAF, etc. Magnetic field assisted MAF, MRF, MFP, and hybrid finishing processes CMP, MRF, RMRF, ECH, ECE and so on. So I have discussed all of them in the earlier slides. Now please try to understand this figure carefully. It tells you the working principle of all these nano finishing processes. Now here is the MAF process. I have just explained it in the earlier slide. Normal force is acting, cutting force is acting over in this direction. Normal force is responsible for penetration and shearing in the form of micro nanochips. You can see here, this is the south pole, this is the north pole, this is the flexible magnetic abrasive brush, and these are the lines, magnetic lines of forces. So abrasive particles and magnetic particles or ferromagnetic particles of carbonyl iron particles, they are in this particular brush. So if they are not sintered, they are loose abrasive particles and magnetic particles, they align and form what is known as flexible magnetic abrasive brush. When you are rotating it, then abrasive particles which are in contact with the workpiece surface, they shear off the peaks of the workpiece surface and they give a nano level surface finish. The best surface finish achieved by MAF by late Professor Ranga Komanji was around 8 nanometer. AFM process, very good process, developed by Extrude Horn of USA, and you can see here, this is the medium, this is the upper cylinder, lower piston, upper piston, and here is the workpiece over here. When this medium, which consists viscoelastic medium, not viscoplastic, viscoelastic medium plus abrasive particles. When it is moving up and down, abrasive particles come in contact with the rough surface of the workpiece over here, and as you can see here, normal force is acting on this abrasive particle, tangential force is acting on this abrasive particle, and fluid is moving up and down. So as a result of that, the peaks like these peaks are sheared off from the workpiece, and you get nano level surface finish by abrasive flow finishing or abrasive flow machining process. The beauty of this process is that very hard material can be finished, complicated materials can be finished in one go. Then MRAP process, which is the combination of MAF plus AFM, it was developed at IIT Kanpur by Sunil Jha of IIT Delhi. You can see here, here is the North Pole, here is the South Pole. This is the viscoelastic material, plus iron particles are also there. So you can see when this magnetic field is there, these iron particles get aligned with abrasive particles either entangled between the chains or within the chains, and when they are in contact with the workpiece surface, they shear off the peaks of the workpiece surface. As you can see here, this is the abrasive particle, normal force is acting which is responsible for penetration, and shear force is acting for removing these irregularity in the form of micro nano chips, and you can get very good surface finish. It is combined with these two processes because this process cannot be used for complicated components, but in AFM you don't have external control of the process. But here, when you are using the electromagnet in place of the permanent magnet, you can externally control the MRAP process, and you can finish hard, very hard materials and even the soft materials. The force that is acting on the workpiece by these abrasive particles can be controlled externally. Magnetorheological finishing process, this process by developed by QED of USA, and they claimed that they were able to achieve surface finish less than 1 nanometer. And you can see here, this is the lens which is to be finished. I will explain later on in another lecture. And this is the fluid which is consisting of iron particles, abrasive particles plus liquid, and when it comes in contact with the lens, abrasive particles are in contact with the lens and they are shearing off the peaks of the lens, and they claim that they are able to achieve few nanometer surface roughness on these lenses. Here you can see the schematic diagram. Electromagnet is there, so you can control externally. MR fluid, magnetorheological fluid is there. This is the conditioner, pump is there which is supplying the fluid, and here you get the ribbon like structure formed on this, and here is the magnet, so magnetic field is there, and this is the lens to be finished. This lens is rotating and ribbon is also moving on this wheel, and the abrasive particles are finishing this particular lens, which you can clearly see over here. This is the lens which is being finished, and after finishing, this fluid is sucked, pumped, and it comes to the MR fluid conditioner where conditioning takes place, and then it is recirculated. Chemomechanical polishing, again chemical reaction takes place, and here you can see this is the wafer phase. Here you can see, here is the wafer, silicon wafer is there, this is the wafer, and this is the pad which is having the slurry. Slurry is being supplied continuously to this pad, and this is rotating in this direction, this is also rotating in this direction. You can rotate one of them in the opposite direction to increase the velocity, and when slurry comes in contact with this wafer, silicon wafer, abrasive particles are there in the slurry, and they remove the peaks of the wafer and shear off, and you get very good surface finish. And this process is very extensively used in electronic industry. You can clearly see here, this is the abrasive particle This is the workpiece, that is the wafer over here, and when they come in contact, they shear off the peaks. These abrasive particles are of nano level, nano size, few nanometers are there. And then all these processes that I have just shown to you and discussed in the earlier slides, they are very good for flat surfaces, cylindrical surfaces, hollow surfaces or complicated components, but they cannot finish spherical components. And this is the process magnetic fluid polishing, which is good for finishing spherical components. And you can see here, this is the magnetic fluid consisting of abrasive particles. This is the drive shaft, little downward force is applied so that this is forcing the fluid. These are the balls to be finished, and here is the bank of magnets, north south pole, south north pole, and so on. You can use the electromagnet also over here. And when you are rotating this spindle, then these balls come in contact with the abrasive particle in this fluid and they shear off the peaks, and you get very good surface finish, and sphericity, circularity is also improved of these balls. I will show you in other lecture. These are the ceramic balls which cannot be finished otherwise so easily. Now, with this introduction to different nano finishing processes, let us see very important application of these nano finishing processes. Now, you can see this lady with so many implants are there. You can see bone screws are there, hip joint is there, spinal implant is there, and here dental implant are there, and knee joint is there. You can see over here knee joint and instrumentation, and this is the shoulder joint. So different joints are, many more joints are there in the human body, and many times because of the accident they break and they have to be replaced, or sometimes in natural phenomena they wear off, shear and tear off, and doctors have to replace it. Now, when you are replacing these implants, the surface finish of these implants is very important, and better the surface finish, more comfortable will be the patient and higher will be the life of the implant. So, we have done some work at IIT Kanpur regarding the finishing of these implants, definitely certain implants. Most of these joints have friction to play its role in some form or other. Reduced friction, because there is a relative motion in the joints, in all these joints there is a relative motion, and once you have relative motion, definitely friction will be there. So, reduced friction will definitely lead to comfort to the patient, longer implant life, natural or artificial, and it minimizes the need for the next replacement. In this case, nano finishing comes to rescue. To rescue means for having the reduced friction. In this case, nano finishing comes to rescue, that is, if nano finishing is done, it will reduce the friction. 3D printing, manufacturing or additive manufacturing can be employed for matching the parts with individual patient's anatomy. This is very important, because what you normally get in the market is definite size, just like a Bata shoes, 8 number, 9 number, 10 number, there is nothing like 8.25 or 8.5, but in human implant you cannot afford it, otherwise it will not work properly, and for that purpose 3D printing plays very important role. 3D printing manufacturing is easily adaptable for minor changes in the size and shape of a part. That part is implant as per patient's anatomy. So, this is very important. But after making a part by additive manufacturing or 3D printing, you need to perform finishing operation in almost all cases, because surface finish is going to play very important role in these implants. Let us discuss very important finishing process that is named as abrasive flow finishing or abrasive flow machining process. Applications are flat, cylindrical, internal and external surfaces, complicated shape, 3D turbine blade, etc. It is very difficult to finish turbine blade, but by this particular process you can easily finish 3-dimensional turbine blades. So, nano finishing, this abrasive flow finishing process is good for nano finishing. It is also good for deburring purposes. I have mentioned this in the case where I was discussing electrochemical deburring, and also good for radiation purposes. Now, how to do deburring inside the two meeting surfaces? Because whenever you are performing conventional machining or even some of the advanced machining processes, then you get the burrs and you cannot use the part in the assembly or directly which is having the burrs. So, how to do deburring inside the two meeting surfaces with required surface finish of the job? That is the question. You can see here, this is the IC engine part. There are many holes drilled, many intersecting surfaces are there inside this, and they are not accessible to the human being, either to the drilling tool or drilling wheel or drilling rod or grinding wheel. They are not accessible to the grinding wheel or grinding rod or grinding tools. So, this engineer was in trouble how to finish them and how to do the deburring. So, you can see here, then some problems in nano finishing of complex shapes, especially unreachable place where you cannot take the component, you cannot take the grinding or finishing tool over there. Internal geometry is complex, so you cannot finish it, you cannot deburr it, and farm tools cannot reach to the location where from you want to do the deburring or you want to do the finishing. So, this gentleman is just thinking about the solution for this problem, and he comes to with an idea of abrasive flow machining process, and he becomes very happy. You can see here, material can be removed in the form of small chips by random cutting edges with indefinite orientation and geometry, because when you are doing with the abrasive particles, they are having random orientation and geometry is also not well defined, with shape changing form, and continuously as the shape of the component is changing, the shape of the medium is also changing. I will show you the picture. So, abrasive flow machining was the solution for this engineer. Classification of abrasive flow finishing: one-way flow AFM for partially through cavity, two-way flow AFM for through cavity, and orbital AFM for blind cavity. We will see pictures over there. IIT K and CMTI Bangalore collaboration abrasive flow finishing machine was designed and fabricated at CMTI Bangalore. So, this is the machine which has been fabricated, very good machine and having special features even better than what was being supplied earlier by extrude horn, and nowadays it has been taken over by VDI. And this is the another picture, and beauty of this machine is that it can also control the temperature of the medium, that is a abrasive flow finishing medium which is consisting viscoelastic material and abrasive particles. Now, abrasive types of abrasive flow finishing, as I showed you in the earlier slide. This is the one way. You are feeding the medium from here, and this is the workpiece which is to be finished. It comes out of it and it finishes the workpiece. And here you have to optimize the parameter about the pressure, about the size of the abrasive particle, type of the abrasive particle, viscosity of the medium and so on. Now again this is one way AF flow AFM. Now you can see this is the cylinder which is having hundreds of holes, and these are the micro holes. You cannot finish them by any other method except abrasive flow finishing process. And here the surface roughness of these holes surface is very important. It controls the process parameter, and all these holes can be finished in one go by this particular process. Here orbital abrasive flow finishing process, you can see this is the tool, this is the workpiece, and here the medium is being pushed, it is moving up there over here. This is the tool which will come downward, and it will force this medium to abrade this workpiece surface. This will come in contact with this medium, and this medium is moving either way, this way or this way, in the orbit fashion. As you can see here, this is showing the rotation, and it can finish this workpiece very nicely. And this is from the courtesy of Extrude Hone Corporation. This process was first time initially developed by Extrude Hone USA, and this is the one which I have explained you earlier also, so I need not to go. This was the setup that was developed at IIT Kanpur, and we were fortunate enough to develop it within 3 lakhs of rupees, while market value of Extrude Hone was around 60 lakhs at that point of time. Nowadays it is more than 1 crore. So this was designed and fabricated by Dr. R.K. Jain, Dr. Sunil Jha of IIT Delhi. Now two-way flow AFM process, and these are some of the components. They were finished to the nano level by this two-way flow abrasive flow finishing process. AFM medium acts as a self-deformable stone, very important and very interesting. I have shown this slide to you earlier also in the introduction lecture, but let us see it again because we are discussing the process. Can you finish following shapes and holes by traditional finishing processes? My answer to this question is no. Now this is the complex shape component, and this is the abrasive flow finishing medium having abrasive particles, viscoelastic medium, and when it is moving up and down, all these faces of the component are finished simultaneously to the nano level surface finish. This is another very complicated shape, and this surface is equally important to be finished, this as well as this. So abrasive flow finishing process is the one which can finish them in one go by moving the medium up and down, but here you have to optimize the viscosity of the medium so that it can reach up to the end of this, as well as also you have to optimize the pressure and other parameters definitely. And this is internal, this is the external surface which has to be finished. This also can be finished by this very easily by optimizing the parameter. Now here is a complicated case. This is actual turbine blades, and this is having the turbulated holes. This hole size is over here, and this we made at IIT Kanpur, these turbulated holes, first time in the world. And now the question was how to finish these turbulated holes, because the maximum size of this hole is 1 millimeter. Most of the places the size is in micrometer. So the question is such a, and this is used in the turbine blades, and they are basically used for cooling of the turbine blade. These are known as cooling holes. So how to finish them? Then this is the process, abrasive flow finishing process, which can easily finish them. You can see IIT KANPUR fabricated another picture of the hole that was drilled in the turbine blade material which we achieved from the bark Bombay, Mumbai. Now this I have already explained to you. Two forces are acting, normal force and cutting force, and once this is there, what is the magnitude of the force will depend upon the viscosity of this medium and the pressure that is acting on this. And when it is moving downward, it is shearing of the workpiece material and removing the material in the form of micro nano chips. Now this I have already shown to you. Now you can see here, this is the working model of this particular process, and you can see this medium is moving up and down, and this is the workpiece which is being finished, and this is the cooling or heating taking place. You can control it with the help of this. This heating and cooling elements are also there in this one. Depending upon the temperature of the medium, there is a controller which is fixed in the machine developed by IIT KMTI collaboration at Bangalore. Piston silly putty, also known as silly putty, it's viscoelastic material plus silicon carbide abrasive. You can change or you can use different types of the abrasive particles depending upon the hardness of this particular workpiece. Then workpiece held in fixture, this is the workpiece, and thermostat for temperature control. This is the thermostat which is controlling the temperature. Please note it, control of the temperature is very important in this particular process. Otherwise, you will not get the desired results on the finished surface. So you can see a tube having a large number of mini holes, delivered and finished simultaneously, courtesy CMTI Bangalore. This is a tube having large number of holes and they are simultaneously finished and burned. Anyway, I am not discussing it here, so let me forget about it. Focused iron beam machining process. How to enhance the performance of abrasive flow finishing process? Alternate 1, centrifugal force assisted AFF process. You can enhance the centrifugal force by rotating these rods over here. This is the rod, it can have different shapes. Centrifugal force guided rod. This is the rod, triangular rod may be there, this shape of the rod may be there, rectangular may or square may be there, rectangular may be there. Now what is happening here is this rod. When this rod itself is rotating, then the centrifugal force on this medium will increase or change, and once this centrifugal force is there, abrasive particles are here over there and they will be in contact with the workpiece surface and they will shear off faster if larger shearing force or centrifugal force is acting over there, and they will shear off and it will increase the performance of the abrasive flow finishing process. Deflection of abrasive particles in centrifugal force assisted abrasive flow machining process. This is the analysis done. Centrifugal guided rod is here and this is rotating, and you have the VA and VC, and this is the resultant velocity which is working over there. Alternate 2 is spiral polishing method, drill bit guided AFF process. Now here this is the drill bit and this is the workpiece to be finished. This is the fixture over there. Now when this medium is there and drill bit is rotating, then the workpiece will get finished faster, because by rotation this here the medium is there. You can see here this medium has come over there, and if it is rotating, it applies additional force on the abrasive workpiece through the abrasive particle. These are the abrasive particles, and you will get the enhanced performance of the process. So this is very interesting to enhance the performance with the help of the rotating drill bit. Some work was done in this direction at IIT Kanpur. This setup was developed at IIT Kanpur while working for abrasive flow finishing process. Possible flows in drill bit guided abrasive flow finishing process. Now this is the animated picture. Now since here fluid is there, so medium can flow over this and this may flow less over here, and you can have the differential velocity which will help in faster finishing of the component. You can see here, this is the workpiece, this is moving up, medium is moving up, and this is rotating also, because this drill bit is rotating, so additional forces of on abrasive particles will be acting over here. This you can see, this is the kind, it is medium is moving like this, while moving up this, and it is rotating also. So both kinds of the forces are acting simultaneously, and you are able to enhance the surface, you are able to enhance the performance of the AFF process. Abrasive direction in the AFF process, these are the abrasive directions or scratches formed due to the abrasive flow finishing. Please note it, these are highly enlarged pictures over here. So don't get confused that they are such a rough surface. No, it is not highly rough surface, it is a finished surface, but the pictures are highly exaggerated. When you are using this drill bit guided AFF process, you can see some marks are there of contact length of abrasive drill bit guided AFF process, and some scratches are there due to the rotational speed of the abrasive particles, and the depth of these may get decreased over there to some extent. You can see over here, this is the AFF process and this is the drill bit guided AFF process. So percent change in surface roughness value, drill bit guided AFF process is giving much better performance than the normal AFF process. This is the normal AFF process and this is the drill bit guided AFF process. Rotational abrasive flow finishing process. You can see here, this is the setup that was developed at IIT Kanpur, and you can see this pulley is there. This is the tooth gear, and here is the another gear, and you have this is the pulley one, another one, and both are connected by the belt, grooved belt, and this rotates. So this is rotating either the workpiece or the medium is rotated if you are rotating the fixture. So depending upon the conditions existing over there, you can rotate the fixture or the workpiece and you can enhance the performance of the process, and that is known as rotational abrasive flow finishing process. This was designed and fabricated at IIT Kanpur, this particular setup, and it enhanced the performance substantially. Motion of active abrasive grain and finishing forces in RAFF. In normal AFF, motion of the abrasive particle is vertical like this, and they are shearing of the peaks of the workpiece surface. As you can see over here, microchip is there, workpiece is here, abrasive particle is there, axial motion is there, and this is the medium. But in rotational abrasive flow machining process, you can see these abrasive particles are rotating all around the workpiece surface like this. You can clearly see here like this. And so what is happening in one up and down motion itself, the contact area of an abrasive particle is substantially increased compared to normal abrasive flow finishing process. That's why the performance of the rotational abrasive flow finishing process improves in terms of material removal rate as well as surface finish obtained and surface texture obtained. I have shown to you some scratches of this rotation in the earlier slide. So you have helical motion of abrasive and microchips are produced over there. So different forces are shown over here. These are the peaks and these are the abrasive particles which are moving in this direction, and they are removing micro nano chips. They are shown over here. You can clearly see here as well as here. So depending upon the depth of penetration, they are removing the material in the form of micro nano chips, and this is the cutting force Fa square plus Ft square under the root, that is giving cutting force, and this is the alpha angle tan inverse Va over Vt. I have already shown to you what is Va and Vt. They are shown over here. Fa is the axial force, Fr is the radial force, Ft is the tangential force, alpha is the semi cross hatch angle, and in RAFF process Fa is assisted by Ft. So, material removal rate and delta Ra are increased. Experimental helical path and its effect on the workpiece surface. This is the kind of the helical path they are attaining for different RPM. If you are having 2 RPM, 4 RPM, 6 RPM, 8 RPM, 10 RPM, so that number of rotation per minute increases, and accordingly the path is increasing, and it is resulting in larger contact area for each abrasive particle. So, you can see here these are the honing angle, micro scratch during active grain downward movement, they are shown over here, and micro scratch during active grain upward movement. If it is moving up, this is the, so you can have the cross hatch pattern over the surface. You can see initial surface 900 nanometer, and this is the 2D, this is the SEM sketch. But after finishing, my God, it has come down to 7 nanometer, and you can see the final surface finish, and this is the 2D sketch. So, you can see it, how much is the reduction from 900 nanometer to 7 nanometer, substantial reduction in the surface roughness value. So, you are having very, very good surface finish by this particular process. Material removal mechanism in MMC, metal matrix composites. Now, machining or finishing of composite had always been a big problem, because you are having more than one material, and each material has, or each constituent material has different properties, thermal properties, mechanical properties, magnetic properties, and electrical properties. So, it creates a lot of problem while finishing. You can see here fractured reinforcement is over here. This is the base material, and you can see the valley due to reinforcement pull out. So, such kind of problems are always faced while you are finishing the composite materials or metal matrix composite material. You can see the mechanism that is acting over there. This is the force acting on this particular abrasive particle, and this is the chip or the microchip being removed, and this is the crater being produced on the workpiece surface. This is aluminum alloy, silicon carbide, metal matrix composite, and this force Fa square plus Ft square under root should be greater than the required force to remove the material. Otherwise, material removal rate will be almost 0. And if it is with the hard material or with the base material, that will decide what kind or what shape of this crater you are going to achieve. You can see a abrasive attacking direction. This is the abrasive that is attacking direction, and it comes in contact with the hard material, harder material or alloy. So, penetration decreases or this gets pulled out. So, it will create the crater over here. So, reinforcement brittle fracture takes place, depends upon what are the properties of the reinforcement, whether it is hard or tactile. Now, fragments of the reinforcement, this part of the fragment part remains over here in the workpiece, part of it is removed from there. So, all this depend upon the properties of the workpiece material, and you can see abrasive attacking direction, and these are the shown over here. So, different locations abrasive particle will come across different conditions. So, you can see here is a comparison for aluminum alloy, silicon carbide 10%, aluminum alloy, silicon carbide 15%, and the performance is completely different. So, you can see all the three cases, they are varying in different ways. Comparative study of performance of RAFF with AFM. On this side it is AFF, On this side it is RAFF, and you can see delta RA, that is change in surface roughness, is much better in RAFF as compared to AFF. This is AFF on this side, and on this side RAFF. Same is true over here. So it gives better performance. Mechanism of finishing of MMC control, I have shown to you these figures in the earlier one. You can see this is the abrasive particle, this is the microchip for aluminum alloy. Here Fa is greater than required force. So you are able to remove the chip material in the form of the microchip. Here Fa is smaller than the required force, the force acting is smaller than the required force. So the material, this is the abrasive particle, and this Fa is smaller than the required force, so it is not able to remove any material from the workpiece over here. As you can see here, it is removed as a microchip. So this is the difference when Fa is greater than F required or Fa is smaller than F required. Rotated abrasive particle is there. This abrasive particle is rotating, and this is the Fa, and this is, when it is rotating, sometimes depth of penetration becomes smaller and it removes the material from here. Earlier depth of penetration was this much. When it has rotated, depth of penetration has gone down to this only, and it is able to remove this particular material while it was not able to remove this material. So that is the advantage of rotational abrasive flow finishing process also when this abrasive particle is rotating. Fa, tangential force in MAF, and axial force in AFF, MREF. Now in composite materials it normally happens, and it is not necessary that it is always there in rotational AFF process, otherwise also it may take place depending upon whether if this abrasive particle rotates or moves, then it can remove the material from this, not from this. Applications, you can see very interesting applications over here. Finishing of turbine blades, these are the turbine blades, and all of them can be finished in one go by AFF process. And finishing of holes over here, these are the small holes shown over here, and all these holes can be finished in one go if you are able to make proper fixture. And these are the small complicated intersection inside the pipe. These are the gears kind of the things, they can be finished, all of them, internal surface as well as external surface. And in this pipe you can have many intersecting surfaces, and if you are able to design the fixture properly, all these intersecting surfaces can be finished in one go by abrasive flow finishing process, which you cannot do otherwise by traditional or even advanced finishing process, other processes. This is the setup again developed at IIT Kanpur. Variable frequency drive, VFD is there, upper hydraulic cylinder, upper medium hydraulic cylinder, medium cylinder, workpiece over here, lower medium, lower this one medium cylinder, and this is the lower hydraulic cylinder. Other devices are there. Conclusions. There is a need of serious dialogue between the researchers working in the field of nano finishing technologies, end users, public and private sectors both, and government, so that the in-house developed technologies can be more effectively used for the benefit of the nation. There is enough scope for the utilization of the in-house developed nano finishing technologies in the strategic areas such as defense, aerospace, nuclear power plants, automobiles, biomedical implants, etc. There is a need for the young scientists, engineers to come forward and interact with the end users and to work in these kinds of highly interdisciplinary areas. Here I will specifically like to mention that engineers working in this area should definitely get in touch with the doctors, orthopedic surgeons, dentists, etc., so that they can help the implants being finished up to required or even better than the required surface roughness value, so that they are helping the patients directly as well as indirectly. Based on the nano finishing techniques discussed here, it is concluded that simple and complicated components can be finished to nano level surface roughness value by using an appropriate finishing method. Thank you very much.